Okay. All right. Well, this is where we left off last time. Just to be, like when we were doing it, when we do a search through, any questions? Last chance before I get going again. When we do a search through a regular binary tree, the item could be to the left or to the right. So when we do a search through it, and we do it recursively, the idea was, is the current node the thing I'm looking for? If it's not, look over here. And if it's not over there, look over there. Okay? But with a binary search, it was a little bit different. Because I could say, because remember, the whole property of the binary search is for every tree and subtree in the tree, everything to the right of it, to the left of it, is less than the node. And everything to the right of it is greater than, or equal to if we allow duplicates. And again, it doesn't matter if it's less than or equal to, or greater than or equal to, as long as you're consistent with one or the other. So, when I'm looking for something with a binary search, I look at the current node, and if it's not the thing I'm looking for, with the regular search through the tree, it could be over here or it could be over here. But if I'm looking for a number that's less than the value I'm currently looking at on the current node, if it exists in the tree, it must be over here. If the value is greater than the current node I'm looking at, then it must be over here if it exists. So before, with the regular search through the tree, it was look over here and then look over here if you need to. With the binary search, it's not that. It's look over here or here, but never both. You'll never have to look at either. You only need to look down one of the subtrees. And that's where this search gets so much more effective, computational-wise. So if I'm looking for the number 19, for example, and I start at the root node and say 14, I know that if 19 is in this tree, it must be in the right subtree of the root node 14. It must be there. And it must be there because it's greater than, and assuming we followed the binary tree property correctly, if it's there, it's over on the right side. That's it. There's no ifs, ands, or buts about it, right? It should be pretty clear. If it's not, ask now. Ask for clarification now. Now, there's no guarantee that it is there. I could say, look for the number 29. There's no 29 in that tree. But let's think about how we would do this search. You look at the 14. Is 14 equal to 29? No. Okay, well, 29 is greater than 14, though, so it must be in the right subtree if it exists. So we look at 26. 26 is not 29, but if it exists in this tree, it must be to the right subtree. We go to the right subtree, it's empty. Then I can conclude it's not there. Because if it existed, it must be to the right of 26. If nothing's to the right of 26, it's not there. It almost feels like, if you're following along and you feel pretty comfortable with what I just said, it almost feels like stupid explaining it, because it's like, yeah, obviously no shit. If it's greater than, it must be to the right. There's nothing to the right, therefore it's not there. It almost feels silly to like explicitly state it, but let's make sure we're being clear about things. Any questions about that? This will only work if it's a binary search tree, though. As soon as you have something that's less than 14 to the right side of 14, it ain't going to work anymore. It's not going to work. So by having a binary tree that has the special property of everything to the left is less than, everything to the right is greater than, we can do things more effectively. Or maybe effectively isn't the right word, but we can do a search through this tree easier. Questions, thoughts, concerns, comments? All right. So yeah, and here's the binary search, right? We have that thing where we have that public helper method. All it does is call the recursive one with the initial state that we want to call it on. And then the actual private recursive one is, well, if the current node is null, it's not there. if the current node contains the thing we're looking for, and remember, compare to gives us 0 if they're equal. So if the comparison is 0, if the result of doing the comparison is 0, then, well, we found it. Otherwise, if it's greater than, then it must be in the left subtree, if it exists. See how I could have written this a variety of different ways. But see how here, it's an if or an else. If this, do this, otherwise do that. Only one of these will ever get called. For every time this method is called, binary search, it's only possible to have it call one more binary search for each time. Here, we call contains, both can get called. Big difference. So this one might have 1 or 2 or none. This one could only have none or 1. It can never recursively call 2 more methods from one call of the method. Subsequent calls can call additional ones, but only ever 1 max. So it's very similar to what I'm dubbing the naive search, the search through a general arbitrary binary tree. It's very similar, where the idea is this the current thing? Look over here or look over here. It's the same idea, but we're leveraging the fact that we know how the data is structured in the data structure. You look at the current node, but you do the comparison to know where it should be, and then you call one or the other. But they're very similar, but it's important to note the differences. Yeah, I just worked through a lot of that. So binary search tree operations. Remember how, okay, if we made the interface, we want to add, remove, contains, a couple of iterators, toString, right? A couple of those things in there. So let's start seeing what an add would look like. Adding is going to be very similar to a binary search. Basically, if you want to add something, do a binary search for the thing you want to add, and then whenever you find an empty spot, that's where you add it. That's the idea. So here's some like pseudocode for it. If the node does not exist, insert the new node here with the element to be added. If the node exists, well, if the element is less than the node, call add on the left child. Otherwise, call it on the right child. That's the idea. So let's use this tree for an example. If I want to add the number, let's say 20, where do I go? All right, well, 20. 20 should go to the right of 14. Now we look at 26. It should go to the left of 26. Now we look at 19. Well, it should go to the right of 19. We see 23. Well, it should go to the left of 23. Go to the left of 23. Nothing's there. That's where we add the node. If we allow duplicates, and following the rule that we're going to follow here, where duplicates go to the right, let's say I'm adding the number 26. I look at 14. Okay, 26 should go to the right. I look at 26. It's a duplicate, but duplicates always go to the right. So go to the right. There's nothing there. Add 26 to the right of 26. So 26 would go right here. It's a binary search, but instead of just returning like true or false, it just actually does the inserting. Any questions about that? Yes?
So if we're adding another 19, it would go down to the left of 23.
Yep. Which is kind of weird, right? But think about it like this. To clarify, the point being brought up, where would the number 19 go in this tree? Well, it should go to the right of 14, to the left of 26, to the right of 19, to the left of 23. Which is kind of funny, right? Because wouldn't the duplicates be? No, that's not a rule. The duplicates don't need to be chained along or anything. All that matters is that duplicates are added to the right-hand side, if we follow that strategy of always going to the right. But also remember, with any of these trees, and remember, every subtree in a binary search tree is itself a binary search tree. And remember, the smallest number, and similarly this will be true for the biggest number, you just flip it, the smallest number in any binary search tree is going to be the leftmost node. So, imagine there was a 19 coming off of here. Okay? The right subtree of the node with the above node, the node that are like with 19 that's already in there, its right subtree would be 23, 19. The leftmost node must be the smallest thing. And so there's a lot of cases where duplicates won't necessarily be immediately to the right of its duplicate. Because the left, I want to make sure because the logic is very clear, so I want to make sure it should remain clear. I've got some node, and I want to add a duplicate, okay? If we allow duplicates, let me grab a marker. I've got some node with, and this might not even, this could be, who the hell knows, right? It doesn't matter. But here's some arbitrary root of some subtree. It could be a whole tree, it could be a subtree, it doesn't really matter. But we have the rule that duplicates always go to the right. Given that, I don't know what's over here, but if duplicates are to the right, what is the smallest and there's a very precise answer you can give me here. This one has a value of x. That's an x, if it wasn't obvious. I'm not making it worse. There, it's an x. All right, it's way worse now. That has a value of x. If duplicates always go to the right, what is the smallest possible value that could exist over here? X. Meaning, x better be the leftmost, if they're like the leftmost node in this subtree, if there's an x over here, it better be that. Right? It's not possible to have a number less than x over here. Because if there was a number less than x, it would be over here. Otherwise, it ain't a binary search tree. Clear? But very good observation. All right, binary search tree add. Yeah, there we go. Okay, starting the existing, if I wanted to add 13, there, that's where it would go. So here's some examples. Add 26 for an empty tree. Well, it just goes there. Add 15, it goes to the left. 38 goes to the right. 31 to the right, to the left, and so on. As discussed a little bit before, the shape of this binary search tree will depend on the order that the elements are added to the tree. The order that elements are added will have a huge impact on what this tree actually is structured like. Remove, min, remove, max. So let's start doing some removes. A general purpose remove is actually rather tricky. But removing the minimum and removing the maximum are actually not too bad. When we're looking for the smallest the smallest value, there are a couple of cases. the leftmost node is the root, which is entirely possible, right? And if that's the node we want to remove, how do we deal with that? There's another case where what if the leftmost node is a leaf node? It has no children. Okay, well, how are we going to deal with it in that case? And what if the leftmost node is an interior node? What do we do in that case? Well, finding the minimum is very simple. And this goes for finding the largest value. Finding the minimum is go to the left, go to the left, go to the left, go to the left until you can't anymore. Just keep going to the left. As soon as you run out of nodes, there, you found the leftmost node. Now we got to remove it. But we might have a couple of cases. Removing will be a little trickier. Yeah, so in add, whenever we add something, it's going to end up being a leaf. Okay? But when we remove something, we might be removing something that has children that need to get addressed, figured out. So that's, removing can get sticky with these binary search trees. So we have to be very careful how we remove, because we need to remove the elements from the tree such that the binary search tree property is preserved. We can't break any of the rules about everything to the left must be smaller, everything to the right must be bigger or equal. So consider the following example. If I want to remove the minimum, I want to remove the number 7. This is one of those three cases where 7, it's not a leaf node, it's not a root node, but it's an interior node. It's the root of some subtree, but it's an interior node. So what do we do in this situation? Obviously, you can see what we do in this particular example, but I'll give you a moment. I want you to take about a minute and try to generalize this problem. This is an example where 7 is the root node, the minimum number. It's an interior node, and it's the minimum of this whole tree. But I want you to generalize this, where 9 is a leaf node, but imagine 9 had more children too. What is a general solution to this problem? And I want you to take about a minute and think about it and convince yourself that, yeah, that's fine. One thing to notice immediately is if 7 is an interior node and it happens to be the leftmost node, is it possible for the minimum to have 2 children? No. It'll either have no children, it's a leaf, or has 1 child at most. It can't have 2. The reason it can't have 2 is, maybe let me flip this explanation. It can have at most 1 child, and the minimum node, if it has a child, it must be a right child. It's not possible for the minimum node to have a left child. Because if it did, what would that mean? It's not the smallest. If it had a left child that existed, that means there must be a value in this binary search tree that is in fact less than 7, meaning that should have been the minimum, not 7. So it must have at most 1 child, and it must be the right child, meaning all of the numbers to the right of this 7, whether there's 1 node here or a billion nodes down here, I don't care. All of those numbers must be greater than or equal to 7. But I also know they must all be less than 15. Because if they were to the left of 15, but to the right of 7, that means I know they're between 7 and 15. So it is safe to promote, for lack of a better term, 7's, the minimum nodes, it's safe to promote the minimum node's right child to be its parent's node's left child. So it is very safe to make it that. Did we intuitively work through this like proof, for lack of a better term? Like, is it intuitive? Are there any questions? Should I go through it one more time? Okay. If we have the case where, okay, let's remove the minimum now. I want you to remove 9. What do? Just get rid of it. Whenever it's a leaf node, it's actually really simple. There's no children to deal with. If I want to remove the minimum from that tree, just get rid of the 9. If it's a leaf node, there's nothing special to do. Although, spoiler, the algorithm we use for removing, if it's an interior node or the leaf node, is actually the same. Because what's 9's right child? Nothing. So, let's take a step back. When we removed 7, we promoted the minimum's right child to replace it. If I replace 9 with nothing, what do I get? Nothing. So the algorithm is actually the same, which is kind of nice. If I want to remove 15, promote it. Promote the 18. Remove 18, remove 26. The same thing kind of goes with what happens when it's a root node. Well, there will be some algorithmic differences based on how we implement the binary search tree. But the idea is also kind of the same. Just promote the right child. Now, it's possible to be the root node and a leaf node. And if that's the case, just remove it. The tree's now empty. But remember, if the minimum number is the root node, there is no left subtree. There's only a right subtree. And it's safe to promote the right subtree's root, in this case the 38, to be the whole tree's root now. Neat? Happy, sad, unhappy? Surprised? Excited? What are you? How do you feel about this? I feel like that. Good. The exact same thing is going to work for remove the maximum. You just flip everything. If the maximum is an interior node, it can only ever have a left subtree. It can never have a right subtree. So all of the same ideas still work. You just flip it. Any questions? There are some faces in here I'm seeing that I can't tell if you're happy or unhappy. Smile if you're happy. Everyone's happy. That's great. It's good. That looks really forced over there. All right, so there we go. We just worked through the cases. There we go. Are all cases the same? One may notice that the rules for each are actually the same. Yeah. Max and remove max, it's the same. Just flip it. Now the general remove. Remove the number 26. What do? Just start over. That's kind of what you're going for. Hey, I mean, that could totally work. Just start over entirely. Yeah, you're right. Yeah, what could we do? I actually want you, raise your hand if you looked ahead on this topic. Really? All right, good, because this gives me a chance to give you an exercise. I want you to think about, in this particular example, and you'll see that this example is actually, well, I won't say too much, but what do you think we could do? The crux of the issue is we might remove something that has 2 children. right? And how are we going to deal with that? Like, what do we do? And I want to give you, like, I'm gonna sit down, and I'm gonna keep my mouth shut. And if you have an idea, that's good. You don't have to raise your hand. But I'm gonna give everyone a few minutes to look at this and think about it. Actually think about this stuff. And here's something I will say before I have you do this exercise. I feel like, especially in math, when you're doing math, and I may have ranted this to you already, maybe even last semester or even this semester, but I'm going to say it again anyways. I always feel like when I learned math, it always felt like the math that I was taught, maybe it was the way it was taught, or maybe it was me, or maybe it was the concepts. I don't know exactly what it was, but for whatever reason, it always felt like the math was being taught to me in such a way that this was just some divine truth handed down by the gods. And you just have to know this stuff. When in reality, some person just figured it out. Someone somewhere went, huh, and they figured it out, right? And I usually talk about this a little bit remember when I showed you the arithmetic series, how you can kind of think about it and someone, you could see the intuition as to why that expression is the arithmetic series, the sum of all those numbers, right? You could see that, right? And it always left me a little confused because I thought to myself, like, well, why didn't they teach us like the intuition behind the math as we went, right? Maybe it was bad math teachers. Maybe you were lucky and you had a good math teacher who showed you the intuition. I don't know. But it always felt very like handed down by the gods, which didn't work for me. And especially as I started learning more and more computer science, where like in computer science, like, in like math, like I'm thinking like high school, maybe even elementary school, you're taught the process and then you're given a problem. And it always feels very like, here's the input into the process you follow and then you calculate the answer, right? Input, you follow the steps, you tell me the answer. That's like a lot of what the math is. But every once in a while, you get a different kind of math. And programming follows along the lines of this different kind of math, where we kind of flip it on you, where it's, here's the input, here's the output, what is this? Right? Where with math, you were taught that box, the process to follow. Where in programming, it's, what the hell's the process? That's your job. Figure it out. And maybe it was when I learned more programming, I got to see like how all of these steps actually lead to the solution. So the point I'm trying to make here is, I want to make sure you're taking a moment to realize that there's a clever solution to this problem. And you are all absolutely capable of figuring this out. And I don't mean like, oh, the bright ones. I mean, everyone in here is well equipped to figure this out. If I taught you, you should be pretty smart. So, think about this. And remember, you can figure this out. If you don't figure it out in the 2 minutes I'm going to give you, don't feel bad. But I want you to be aware that you can do this. You actually can. It's not some fact that's handed down by the gods. It's something that some asshole figured out and it worked really well. And you could be that asshole too. Did you have a question? Okay. All right, so I'm going to shut up and I'm going to give you a few minutes to think about this. And I want you to rationalize what you could do. And you know what? There's actually a lot of solutions to this problem, but there is a nice, elegant one. Raise your hand if you have an idea. I'm not going to, this is a poll. Really high, I want to see if you have an idea. Okay. There's a couple people that don't. I'm still going to give you another like 30 seconds, a minute to think about it. But I don't want you just having it, like, make sure your idea is like, and here's how I convinced myself I'm right. Like, that in your head too. All right, so, okay, raise your hand really high if you have a solution in your head. This is just a poll. I'm not going to call on you right now. Really high, 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 I want to see. Okay, so, now I'm going to ask a different question. What I want to do is I want to ask a few people to explain their idea. Because there are multiple workable ideas here, to be very clear. And I want a couple of people to say their ideas. So raise your hand if you're comfortable volunteering your idea. No one. One person. Really high, I want to see. One person, two people, three people, three people. Can we get one more? Let's get one more. Four people. Okay. So here's what I want to do. We'll go and each person will explain it. But if yours gets explained, if you're like, no, that's what I thought. Okay, yeah, you don't have to go. So what was your idea?
You could take the whole left subtree.
The whole left subtree.
And just assign 15 as the root. And then you just kind of shift up, I guess.
Okay, in this particular situation, but what if there was like a number like 16 to the right of 15? Then it wouldn't work, yeah. Okay. So what were you thinking?
Like you just move the whole left subtree goes through the root.
My idea is you move up the 38 and get the root, and then you know the left of 26 is always going to be the leftmost thing, so you make it the leftmost thing of the 38 root.
So say that again. Okay, you said move the 38 up.
Yeah, so you already the 26, then you know the left of 26, right, is always going to be the leftmost like chain of things because it's the left of 26. So then you go on the 38, then you set it to the leftmost things.
So you say, so where should the,
So the 15 should be left of 31, and the 7 should be left of the.
so you're doing some rejigging there. Okay, okay. Other idea. What was your idea?
You take just the minimum of the right side, make that the root, and then take 15, just add left of that, and then take everything that was above 31. At the end, you kind of have to set a few of the children to know at some point. But, yeah.
Okay, and what was your idea?
Mine was kind of like the first one there, like the 15 at the top. That's really good.
Okay. So some of these will work in specific cases, but one of them will work pretty damn well in general. It's probably pretty obvious, but yours works pretty damn well in general. But let's talk about this. So first, let's be clear. How much time we got? Good. Let's be clear about what the idea was. You take the smallest number from the right subtree. Okay? In this particular example, it's 31. But the smallest number in the right subtree must be bigger than everything over here because it's to the right of the original root, meaning it must have been bigger than 26 or equal to. But it's also the smallest number in this subtree, meaning everything else in this subtree must be bigger than it, right? So first, it's safe to make that the new root, because everything on the left subtree is still fine to stay in the left subtree unchanged. Everything else in the right subtree, like it should be to the right of 31. Now, there are going to be odds and ends that you kind of have to deal with. It's possible that 31 is an interior node, like it is right here. And if it is an interior node, well, what do? Well, it's the same idea as removing the minimum. You just promote its right child up. Okay? Because 34 must be less than 38. So it's the same thing as removing the minimum. It's also possible, imagine 34 isn't here, that 31 is a leaf node. If that's the case, well, whatever, you move it. It's fine. But it's also possible that, let's say, 31 is where 38 is. It's possible that 31 is the root of the whole right subtree. And if that's the case, well, it's still the same idea as removing the minimum. You just promote the right subchild to be the new root of that whole subtree. Any questions about that? So let's reiterate. The reason it's safe to promote it is if it's the smallest number in the right subtree, it's still bigger than everything in the left subtree, and it's less than or potentially equal to, less than or equal to everything else in the right subtree. So it's safe to make the root, because everything to the right will still be bigger than it or equal to. Everything to the left will be less than it. So that property is preserved. And what do you do with the dangling situation of what happens if you remove the minimum and you've got a dangling thing, like a child that needs to be addressed? It's the same as what we did when we removed the right subtree, promote the right child. Any questions about that? Okay, for those of you that raised your hand originally about having an idea, be honest. Raise your hand if you were like, yeah, that was my idea. No, it wasn't.
I know I messed up. I didn't say something else.
So you had that idea, you had that idea. Anyone else had that idea? What other ideas? Because like you had your hand up. What was your idea? No, him. You already said yours.
Pretty similar to that.
Similar, okay. What was your idea?
I was to move 15, or like the one in the 15 position up, and then if it had any right, to move those to the left of the right side. Like they would be less than 31, so let's put everything.
So they'd be greater than 15, but less than, oh, so basically, so that's like what you call like a rotation. And there's actually a whole thing that we can learn about those later. But so basically, you promote the 15, and if 15 had any children, they'd become the left subtree of anyone over here. Okay, yeah, that's definitely workable. What was your idea?
Promoting 38 to the root, and then just taking the left subtree and moving it down into the...
And then moving, okay, to the other side. Gotcha. All of these are workable, to be very clear. But the one we're going to go with is going to be the smallest thing in the right subtree will be promoted. It's going to be the most consistent. Fortunately, we're not going to be worrying with balancing. So let's take a moment and talk a little bit about balancing. The whole shtick of the binary search tree is that, you know, everything to the right's bigger, less. It's weird because I have to be a mirror. Everything to the left, which is my right, is less than. Everything to the right is bigger. And what you want is you want the height of the tree, like you want the tree to be balanced. You want the number of nodes over here and the number of nodes over here to be as close as possible, right? That's what we mean when we say it's balanced. When it doesn't have a good balance, we call it a degenerate tree. And when it doesn't have a good balance, a lot of the value of like a binary search gets eliminated, because the whole point of a binary search, like the reason why it worked, was every time you made a decision to go right or left or right, you wanted to eliminate close to like as much information as possible from the search. So I want to be able to eliminate half of the things every time. If it's very unbalanced, you're not going to be eliminating half the things every time. In fact, it could be the extreme where it's not balanced at all, which was that one example I showed, I think, last week. So imagine I have some just general binary tree. Sorry, a binary search tree or something, right? Like the furthest a search through a binary tree is ever going to have to go is the height. Okay? That's the furthest it could ever go, because every time you make, like you'll, once you get to a leaf, you're done. So the furthest you ever have to go in the search, the number of decisions you have to make is going to be related to the height. 1, 2, 3, 4. Okay? For the sake of argument, let's just fill this out to have a nice full tree. So how many things are in this tree? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So when the tree looks like this, we'll have to make four guesses. 1, 2, 3, 4. But if the tree is very not balanced, to show you the other extreme of what I mean, like this is perfectly balanced, but there are 15 nodes there. Imagine we had a tree where it just so happened that every time we added something, it always went to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 there. And the same rule applies. It's the number of guesses we're going to have to make if we're doing a search through this. If we're doing a binary search through this, remember, all of these have left subtrees. They're just null. So the same thing applies. The number of guesses we're going to have to make. Both trees, this is a tree, trust me. Both trees have the same number of nodes. And for both trees, the number of guesses we have to make is going to be based on the height of that tree. But what's the height of this tree? 15. So we got to make a lot more guesses. So this is where the idea that you just brought up comes in. We want our trees to be balanced. We don't want that to ever happen. I'm pretty sure, I could be wrong, but I'm pretty sure I don't have you balancing this semester. Maybe I'm wrong. We'll find out in a day or so. But I'm pretty sure we don't balance, because balancing is kind of, we don't really have enough time to go over it effectively with the amount of time we have left this semester. But there are ways to balance. And it's interesting, because you had mentioned something that required like a left-right rotation, and that's actually how you would kind of do a balance. Depending on the certain situations, you do rotations. But there are strategies. There's an algorithm we can follow to balance the trees. Maybe I could be wrong. Maybe we do balance. Oh, well, you'll see. It'll be a surprise. It's been a year since I did this, so I don't remember what we do. Anyways, there we go. That's just saying what we do. The leftmost subtree. Okay, wait, we want to remove 70. Okay. If we want to remove 70, that's easy. So now we're talking about a general remove. Do you have a question? Okay. We're talking about a general remove. If it's a leaf node, easy. You get rid of it. Remove 7. It's an interior node. What do we do? Well, I guess 9 would go up, but notice that 9 is the minimum number in that right subtree. Remove 38. Now this one's tricky. What do we do here? We move 36 up. It all depends on couple of rules. Here, we actually did like the opposite. Both will work. It all just depends on the strategy we want to take, where I actually replaced it with the biggest number in the left subtree. Usually, I would say the best way to decide which way do you want to go, do you want it to be the biggest thing in the left subtree or the smallest thing in the right subtree? It'll depend on what we want to do with duplicates. If we put the duplicates to the left, do that. If you have the duplicates to the right, do it the other way. Both will work, it just depends on what you want to do. Do you see how it's like a mirror though? Either the biggest thing in the left or the smallest thing in the right. Cool. Anyways. Okay, contains a binary search. So if we have n nodes, how much time do we got? You know what? Let's not. Let's stop here for today. Any last questions? All right, I'll see y'all later.